Welcome back to this examination of half-truths about retreating glaciers in part 6 of how pressure systems control climate. Now, there is no question whatsoever that most of the world's glaciers have been retreating. However, because the elites at Climate.gov believe rising CO2 is causing all the Earth's warming, they mistakenly assume it can also be blamed for retreating glaciers, stating, "The most dramatic evidence that the Earth's climate is warming is the retreat and disappearance of mountain glaciers around the world." So the public is fed half-truths about a CO2 climate crisis causing glacier retreat. In contrast, there is a wealth of opposing, peer-reviewed, published scientific evidence demonstrating that the changing patterns of moisture transport control the ebbs and flows of glaciers, not global average temperature. So here I will share just a small portion of that science for you to follow. Just consider that Greenland's Jakobshavn Glacier retreated by half its length before 1851 during cooler times. Clearly, dynamics other than warming are in play. Dynamics shamefully downplayed or not discussed at all by mainstream media. Now, a growing number of scientists have been questioning the dogma that the Little Ice Age's glaciers' growth and subsequent retreat was driven by changing temperature. As Norwegian glacier expert Atle Nesje queried, "The Little Ice Age? Only temperature?" In that regard, climate scientist Michael Mann wrote, "The Little Ice Age was a time of modest cooling of the northern hemisphere by about just 0.6 degrees Celsius. Those centuries may have been more significant in terms of increased climate variability." Climate scientist Christian Vincent questioned why the Alps glaciers began retreating in the early 1800s before any global warming had begun, and concluded decreasing winter precipitation caused glacier retreats. Now, glaciers can be characterized by two different but intimately linked zones. The ablation zone is located at the lower end of a glacier. There, snow and ice are lost during the warm summer melt season. So some scientists argue glaciers are retreating because CO2 global warming is increasing ablation. At the top of the glacier is the colder accumulation zone, where snow and ice are added to a glacier. When there is less replenishment of ice in the accumulation zone due to decreased precipitation, less ice is transported downslope, causing the ablation zone to also retreat. Thus, less precipitation can cause retreating glaciers even when temperatures are not warming at all. A group of Swiss climate scientists, led by Hans-Peter Holzhauser, published that the periods of the Little Ice Age glacier growth in the Alps, illustrated by the black silhouettes, correlated with periods of heavy rainfall and high lake levels, illustrated by the shaded regions. 3 periods of high lake levels corresponded with peak glacier growth, while glacier retreats correlated with lower lake levels. In the paper, Solving the Paradox of the End of the Little Ice Age in the Alps, Vincent reported that our current retreat of alpine glaciers had resulted from a 25+% decrease in winter precipitation since 1830. Norwegian climate expert Atle Nesje argued the North Atlantic Oscillation determined which regions receive glacier-sustaining moisture by shifting the pathways of the moisture-bearing westerly winds. During the oscillation's negative phase, the Azore High and Icelandic low-pressure systems weaken and shift southward, diverting most westerly winds towards the south part of Europe. During the positive phase, those pressure systems intensify and shift the winds northwards towards Scandinavia. So in the positive phase, precipitation is being diverted away from southern Europe, causing its glaciers to retreat, while simultaneously redirecting moisture to the Scandinavian coast, where the glaciers were growing since 1967. Now, the North Atlantic Oscillation can shift phases from month to month, but on average will favor one phase for decades or centuries. During the Little Ice Age, the scientific consensus suggests the North Atlantic Oscillation was primarily in its negative phase, accounting for the growing glaciers in southern Europe. But since at least 1920, it has been in the positive phase more often, accounting for the high percentage of retreating alpine glaciers. Between 1950 and 1980, during a slightly more negative phase of the oscillation, the number of advancing alpine glaciers increased to over 60%. But with a return to a more positive phase, fewer than 5% of the Alps glaciers are now observed advancing, and most are retreating. Now, due to a surprising denial of precipitation effects on glaciers, politicians and climate crisis promoters argued rising CO2 would cause the extinction of Mount Kilimanjaro's glaciers before 2020. However, based on the past lake levels, such as nearby Lake Naivashes, precipitation changes correlated again with the ebbs and flows of Kilimanjaro's glacier. 1,000 years ago, during the medieval warm period, this region of Africa was much drier than today, and the existing glaciers of that time likely disappeared. Then, during the Little Ice Age, coinciding with sunspot minimums, the intertropical convergence zone migrated southward. The region experienced increasing rainfall, and a new glacier evolved, reaching its maximum area by the late 1700s. In 2007, glacier expert Douglas Hardy summarized research indicating Kilimanjaro's current glacier is only about 50 to 200 years old, in agreement with the timing of Lake Naivashes' high stand and refuting previous estimates of a much older glacier. Similarly, research by Cullen in 2006 concluded glaciers on Kilimanjaro are merely remnants of a past climate rather than a sensitive indicator of 20th century climate change. Curiously, over the past 4 years, as sunspots approach century lows, Lake Naivashes lake levels have been increasing, along with increased snowfall on Kilimanjaro. So keep an eye out for how Kilimanjaro responds. It certainly hasn't disappeared as Al Gore or Michael Mann predicted. By ignoring precipitation dynamics of previous centuries, clickbait media uses graphics like this to suggest that the glacier will soon disappear and incorrectly blame CO2 warming. The climate crisis narratives typically fail to report renowned glacier expert George Kaiser's 2010 explanation of that decline, stating, "The near extinction of Kilimanjaro's plateau ice in modern times is controlled by the absence of regional wet periods rather than changes in local air temperatures on the peak of Kilimanjaro." A 2019 study led by Kevin Anchikaitis used drought proxy data to determine regions of high rainfall and snowpack, here illustrated in blue, and regions of drought, illustrated in brown. They found a strong correlation with weak solar output, the sunspot minimums, the negative phase of the North Atlantic Oscillation, and Little Ice Age glacier advances in southern Europe, Alaska, and northwestern America. When the North Atlantic Oscillation changed to its positive phase, wet regions switched to dry regions, with resulting glaciers retreating. Glacier National Park, on the USA-Canadian border, sits at a pivot point of the North Atlantic Oscillation's wet-dry seesaw. The park's largest glaciers, the Sperry, reached its maximum size in the mid-1800s during the wet negative phase. The ensuing drought conditions when the North Atlantic Oscillation switched to its positive phase caused the Sperry to lose 62% of its area between 1850 and 1945. Further north, the mysterious retreat of Alaska's Glacier Bay glaciers highlighted another dynamic. In 1794, the Vancouver expedition reported the entire bay was covered by a large tidewater glacier with its ocean outlet at Icy Strait choked with ice. 85 years later, in 1879, before global warming had begun, John Muir visited Glacier Bay to find the glacier had retreated a whopping 48 miles. By 1916, the bay's main glacier had retreated an additional 17 miles. So why such a rapid retreat in those cooler times? To complicate matters, there are still glaciers that are currently growing despite warmer temperatures. The Johns Hopkins Glaciers has been advancing since 1929. The Marjorie Glacier flows downslope at a rate of 2,000 feet per year, where its terminal maintains a stable position by calving icebergs into the bay. The Brady Glacier had advanced between 1794 and 1961 and is now relatively stable. The key to understanding these contrasting fluctuations is that non-retreating glaciers have accumulation zones at elevations above 10,000 feet or 3 kilometers. Olivia Jacobs' 2021 study of glacier behavior in the Gulf of Alaska since 2010 showed contrasting glacier fluctuations were a function of elevation. Glacier Bay is fed by glaciers in the St. Elias Mountains, shown here in orange. Glaciers originating in the higher elevation mountains are stable or gaining ice over the past decade, as seen by the green trend lines in the St. Elias Mountains and the Alaska Range Mountains. In contrast, glaciers at lower elevations are losing ice, the reds and yellow trend lines. Coincidentally, of the small glaciers that once contributed to the glacier that had filled Glacier Bay when seen by the Vancouver expedition, had accumulation zones below 10,000 feet. Clearly, in addition to precipitation amounts, glacier growth and retreat were functions of elevation. So why is an elevation of 3 kilometers or 10,000 feet so critical at Glacier Bay? Well, snow forms when water vapor freezes, and freezing temperatures are typically encountered at 10,000 feet and above. For snow to accumulate on a mountain slope, local air temperatures must remain below freezing all the way to the surface. However, during the summer, the Glacier Bay's average high surface temperatures are above freezing in August through October, just when peak precipitation occurs. Using a moist lapse rate of about 2.7 degrees Fahrenheit cooling for every 1,000 foot increase in altitude, we can calculate the elevation where snow will accumulate each month. The minimal freezing elevations for August is 10,300 feet, is 7,700 feet for September, and 4,800 feet in October. Now, atmospheric rivers carry the bulk of moisture from the tropics to the higher latitudes. Where atmospheric rivers make landfall is determined by the seasonal position of the Pacific's high and low pressure systems. The more northerly position of the Pacific high pressure system during the summer guides more atmospheric rivers into the Gulf of Alaska during August through October. Accordingly, Glacier Bay's peak precipitation happens during September and October. But landfall of relatively warm atmospheric rivers has dramatically different effects on snowpack at different elevations. Atmospheric rivers increase snowpack above freezing elevations, but reduce snowpack at lower elevations. The near total reduction of snowpack by a warm atmospheric river has been well documented from Greenland to California, Sierra Nevada. Without accounting for elevation freezing points, such contrasting effects of precipitation have caused some correlational studies to mistakenly suggest precipitation has no significant effect on a glacier's overall growth. The moisture transport to the Himalayan glaciers is more complicated. The greatest accumulation of ice in the Mount Everest region is driven by summer monsoons. And similar to northwestern America's glaciers, El Niño and La Niñas cause decadal ebbs and flows of moisture transport to those glaciers. In contrast, the Karakoram Mountains receive little moisture from the summer monsoons, but more moisture from the winter westerly winds, causing the Karakoram glaciers to react differently than the eastern Himalayan glaciers. Nonetheless, a multitude of researchers, such as Shekhar 2017 and Singh 2020, have reported a long-term drying trend that began in the late phases of the Little Ice Age, causing retreating Himalayan glaciers long before the rise of industrial CO2. Now, climate expert Tapio Schneider's 2014 research described how the intertropical convergence zones migrated southward during the Little Ice Age, weakening the Asian monsoon's supply of summer moisture to the Himalayan glaciers. Jianhui Chen's 2019 study detailed how the North Atlantic Oscillation affects the moisture transport to the Himalayas. As the Little Ice Age ITCZ and associated pressure systems shifted southward, a wavier jet stream brought more moisture to the Himalayan and Tibetan plateau via the western winds. As solar irradiance rebounded from its depths during the Maunder sunspot minimum, the ITCZ and associated pressure systems began migrating northward, also driving the jet stream northward and reducing moisture transport to the Himalaya. The interplay of these conflicting dynamics makes it difficult to predict future glacier changes in the Himalaya. Nonetheless, the politically driven United Nations Environmental Program, or UNEP, argues the decline of Himalayan glaciers are a clear indicator of CO2 climate change and an obvious indicator of warming temperatures, and they provide this illustration to support their narrative. However, their bias is immediately obvious. They illustrate a strong decline in 3 Karakoram glaciers, but just one stable glacier and one that is slightly gaining ice. In contrast, glacier expert Melanie Rankel's 2014 study reported nearly 80% of Karakoram's glaciers were stable, 5% were advancing, and only 7.6% were retreating. Furthermore, due to a dearth of long-term surveys, most of the Himalayan retreating trends begin around 1960, and that provides misleading optics used to support a narrative of human-caused CO2 warming. UNEP provides only 2 trends beginning around 1850, and those clearly demonstrate glacier retreats began before global warming. The United Nations is disturbingly spreading misinformation by not informing the public about well-documented drying trends that initiated glacier retreat before rising CO2. But then again, I expect nothing less from an agenda-driven organization that brings a 16-year-old actress front and center to browbeat the public about climate science. Tibet's ancient holy mother, Kwangalangma, also known as Mount Everest, further illustrates why retreating glaciers are a function of less precipitation. As Franco Salerno published in 2015, 75% of Kwangalangma's glaciers reside between elevations of 5,000 meters, which is about 16,500 feet, and 6,500 meters, or over 21,000 feet. This happens because atmospheric temperatures do not drop below the freezing point until elevations of 5,000 meters and higher. Glacier accumulation zones are fed by monsoonal moisture peaking in July and August. Accumulation zones must be above 5,000 meters as summer monsoonal flows raise the surface temperatures at 5,000 meters. However, measurements reveal precipitation at high elevations was just half of what it has been 20 years before Salerno's study. That fact led Salerno to conclude their research challenges the assumption that temperature is the main driver of glacier mass changes. So what does the future hold for the Earth's glaciers? understanding moisture transport, not global average temperature, controls glacier growth suggests that they are not in crisis. A return to the negative phase of the North Atlantic Oscillation would reverse the retreat of many of the world's glaciers. Although glacier lengths may shrink, accumulation zones will survive where there is adequate precipitation. El Niños and La Niñas and other natural oscillations will affect storm tracks, causing decadal ebbs and flows of regional glaciers. But the ultimate control will be determined by solar effects on the ITC's latitude and its associated pressure systems. While changes in sunspots in irradiance are unpredictable, the orbital influence of the obliquity cycle suggests the ITCZ will continue to move southward for another 10,000 years, causing little ice age-like growth of the world's glaciers. Up next, Part 7, Floods. And until then, embrace the advice of renowned scientist Thomas Huxley that skepticism is the highest of duties and blind faith the one unpardonable sin. And if you appreciate the science clearly presented here, science that's rarely presented in mainstream media, then please give it a like, give it a share, or copy the video's URL and email it to friends. Subscribe to my channel to see all my videos, or read my book, Landscapes and Cycles, An Environmentalist Journey to Climate Skepticism. Thank you.